So let's take a look at variance and standard deviation. And these are measures of risk. And another name for risk is uncertainty. So you see here, variance and standard deviation measure the volatility of asset returns. In other words, variance and standard deviation measure risk. The greater the volatility, the greater the uncertainty, or the greater the risk. So historical variance is equal to the sum of squared deviations from the mean divided by the number of observations minus 1. And this is the, if you want to say, the formula for a sample, which means that we're looking at a small number of returns in this case. And don't worry, we will get to the actual calculations later on and in your problem set. Standard deviation is just the square root of the variance. So after you found the variance, you find the square root of that number and it will give you the standard deviation. So let's take a look at an example. So notice here we are looking at returns for just 4 years. This is a sample, and this is why we divide by n minus 1. Some of you may remember this from your statistics class. But let's take a look at how we calculate variance and standard deviation of a sample. So you have the years 1, 2, 3, 4. You have the return for each year, 15%, 9%, 6%, and 12%. The first step is to find the mean or the average. So how do you find the average return or the mean return? You add these up, your total, and you divide by 4 because you have 4 years. So you see that the average return when you add these up and divide by 4 is 0.105 or 10.5%. So that is the first step, to find the average. The second step is to find the deviation from the mean or the deviation from the average. Remember, mean, average, they mean the same thing. So 0.15 minus 0.105 is equal to 0.045. 0.09 minus 0.105 is equal to negative 0.015. 0.06 minus 0.105 is equal to negative 0.045. And finally, 0.12 minus 0.105 is equal to 0.015. Step 3 would be to square the deviations. So 0.045 squared is equal to 0.002025. Negative 0.015 squared is equal to 0.000225, and so on. You're squaring the deviations. And the variance will be the sum of the squared deviations. You add these up. The sum of the squared deviations divided by n, number of years here, minus 1, which is equal to 0.0015, and the standard deviation, remember, equals the square root of the variance. So when you find the square root of 0.0015, you get 0.03873. Many times you'll be asked to report the standard deviation as a percentage. So you don't do that with the variance, but many times you'll be asked to do that with the standard deviation. So in other words, your answer would be 3.873%. So here we have the work the web example. If you want to look at a bit about mutual funds, we actually subscribe to Morningstar here at the library. So you may want to go to the Morningstar database through the library, because you will have more functionality and a wider access to Morningstar. So it's actually a really nice database to play around with and to get more information about mutual funds, about various companies, etc. This here just shows you the distribution of, and like I said, you may take a look in your actual slides, and you will see that on this slide here we have the distributions for the various stocks, large company stocks, small company stocks, bonds, so the various securities. And what do you see here? You see here that large company stocks has somewhat of a wide distribution, indicating higher risk. But take a look at small company stocks, an even wider distribution, more variability around the mean, which tells you, if you just look at the first two, you can see that small company stocks have a wider distribution, which just means there's more risk associated with small company stocks. There's more volatility associated with small company stocks than large company stocks. And as you go down here, you will notice a tighter distribution, indicating less risk. Okay? So a wider distribution indicates more risk, more volatility. A smaller distribution or taller distribution means that there is less risk. So you see here, and again, this is something you would have seen in your statistics class. The normal distribution is a symmetric bell-shaped frequency distribution. And as you see, it is completely defined by its mean and standard deviation. So let's take a look at it. All right? So this is what we mean by a normal distribution. So what we were saying before, small stocks have a wider distribution. So it goes somewhat like this, indicating that there's more risk. So the tighter the distribution, or if you want to say the taller the distribution, there's less variability around the mean, meaning there's less risk. So just some information for you here about recent market volatility, right? Some of you may know that 2008 was one of the worst years for the stock market. The S&P 500 actually went down 37%, and the index or the S&P 500 lost 17% in October alone. And as you may know, many of your parents, many of us lost quite a bit of money at that time. But if you left it in there, the stock market rebounded. As you can see here, from March 2009 to February 2011, the S&P 500 actually doubled in value. In long-term treasury bonds, these are bonds issued by the government, gained over 40% in 2008, but lost almost 26% in 2009. So when the stock market is doing badly, the bond market is actually doing very well, and vice versa. Let's take a look at the arithmetic versus the geometric mean. The arithmetic average is the simple average. It's what we calculated a few slides ago. It's just your normal average. The return earned in an average period over many periods. The geometric average, on the other hand, is the average compound return. So you're actually multiplying in this case. It's the average compound return per period over many periods or over multiple periods. The geometric average will be less than the arithmetic average unless all the returns are equal. And which is better? The arithmetic average tends to be overly optimistic for long periods of time, whereas the geometric average tends to be overly pessimistic for short time periods. So the answer to the question, which is better, really depends on the period or the horizon that you are looking at. If you're looking at a period of 15 to 20 years or less, then it's better to use the arithmetic average. If you're looking at a period of 40 plus years, it's better to look at the geometric average. And if you're looking at a time period in between these two, then you would split the difference between them. And the reason we're talking about this is really for research purposes. So if you're doing research and you're looking at very long time periods, over 14 years, and you want to find an average, you have to look at the geometric average. If you're looking at 15 to 20 years or less, it's better that you look at the arithmetic average. So let's look at some examples and calculate averages. What is the arithmetic and geometric average for the following returns? And we see here that the arithmetic average is just your normal average. You add these up and divide by 3. The geometric average, on the other hand, I want you to pay close attention to how you do this. It's 1 plus the return times 1 plus the return times 1 plus the return. So you see here, that's why we say it's a compound return. You're multiplying the returns raised to the power of 1 over n. In this case, you have 3. So 1/3 minus 1. And you see here that the geometric average is 4.49%.